Hello and a good day, everyone. Welcome to our EMM 3226 Thermodynamic 1 Group 9 presentation. It is about air conditioning and refrigeration cycle. Before we proceed, I would like to introduce myself. My name is Kitraj Ankeswasulam and my metric number is 211948. So let's get into the introduction of the refrigeration cycle. Firstly, we talk about how it uses the combined gas law, which is the Boyle's law, Charles' law, and Gibbs's law. We're going to focus on the Gibbs's law as it states that the pressure increases, the temperature also increases. So from here, we can see that how does the combined gas law is used is by pressurizing or depressurizing the refrigerator in order to increase or decrease its pressure, its temperature. So we also have involved with first and second law of the thermodynamics, in which the first law is the conservation of energy, and the second law is when the heat is transferred from hot medium to cold medium. An air conditioner works using a thermodynamic cycle, which is also known as the refrigeration cycle. It does by changing the pressure and the state of the refrigerant by absorbing or releasing heat from outdoor to indoor or indoor to outdoor. So we have a vapor compression refrigeration cycle in which we have two parts, which is the actual and the ideal. The actual is always have the lower efficiency compared to the ideal due to friction that causes pressure drop and also the heat transfer. And now we're going to talk about the air conditioners transfer from heat from the indoor to outdoors. Most people think that air cons create cold air, but however, it actually absorbs hot air from the indoor and then flush it out to the outdoor through its a series of processes. So we can say that aircon is considered split system in which yes, an evaporator and a condenser. You can see in this picture that condenser unit is on the outside and the evaporator unit is inside the house. Now we also see the pressure and the versus enthalpy graph. Uh, the pressure remains constant in both evaporator and the condenser state. Next, we move to the refrigerant. We may be used in cooling of fluid in an aircon. We use refrigerant because it can change easily from liquid to gas or gas to liquid due to its low boiling point. And now we're just giving a graphical visualization of the refrigeration cycle in the pipeline. We have four parts: the evaporator, the expansion valve, the condenser, and the refrigerant, and the compressor. And that's all for me. Thank you.
Hi everyone, now I'm going to present about the fundamental principle of first law of thermodynamics related to the air conditioner. First of all, let me explain what is the first law of thermodynamics. First law states that the energy can neither be created nor destroyed during a process. It can only change form. So let me explain how first law of thermodynamics is applied in the air conditioning system. Indeed, an air conditioner doesn't make the heat from a room disappear miraculously, as stated by the first law of thermodynamics. It rather simply lets it go out through an air conditioning system installed through a cycle called vapor compression refrigeration cycle. So let me explain what is the refrigeration cycle. So during the summer days, the main purpose of air conditioner is to cool down a room. That means it will remove the heat from the hot room. So the main components of refrigeration cycle is the tubes of coil that contains coolant. So when the coolant is come in contact with the hot air of the room, it will heat up to a higher temperature until they turn into a gas. This liquid to gas transition will require heat. This heat is come from the hot air in the room. So when the heat is removed from the room, it will cool down. The air in the room is cooled down. So in order for the air conditioner to work cyclic, the system of tubes that contains the gas is placed outside the house, and the heat in the gas is released into the surrounding using metal plates located outside unit of the air conditioner. To turn the gas back to the liquid phase, it is compressed and condensed the, through the compressor and condenser that is placed outside the property. And then this liquid will be returned into the evaporator to continue the cycle. This is how the evaporator and condenser works. So the coolant will take up the heat from the hot air in the room, and then the cool air is released back to the room. While in the condenser, the coolant will release the heat from the metal coil into the surrounding. That's all from me. I'll pass you the next presenter.
Hello everyone, my name is Kiran Rajendran with metric number 211534, and today I'm going to explain about the second law of thermodynamics. So the second law of thermodynamics asserts that the heat cannot move from a reservoir of a lower temperature to a reservoir of a higher temperature in a cyclic process. The second law also asserts that energy has a quality. In the figure below, the energy stored in a hot container with higher temperature has a higher quality, ability to work, in comparison with the energy contained at a lower temperature in the surrounding. The second law is also used to determining the theoretical limits for the performance of commonly used engineering systems such as heat engines, refrigerators, and air conditioners. So the next slide, I will explain about the application of second law of thermodynamics in air conditioning system. So here is the schematic diagram of a vapor compression system. So now I'm going to explain about specifically about the compressor. So the efficiency are essential to measure of the usable energy achieved during a process. Achieving optimum energy efficient is design of a different machines helps to reduce inevitable entropy implied by the second law. Based on the figure in the order accomplished, the refrigeration cycle or compressor is used. To run the compressor, work in the term of energy must be used to compress the refrigerant to the right pressure to go through the condenser. Engineers must design the compressor to yield optimal efficiency, taking the second load into account since the refrigeration of the air conditioning process is not any isentropic. So isentropic is a process with no entropy. Then the amount of energy required to operate the compressor is pressurized. The refrigerant is more than the heat transfer that will occur from the hot room in the hotter outdoor due to the presence of the second law. Engineer can show the process making the loss as efficient as possible to maximizing the energy usage. So here, uh, so thus we can conclude this with a formula which is the electric input, which is E equals to compression work output, which is W output plus the heat output, which is the Q out. So that's all from me. I will hand over to the next presenter.
Hello, now I would like to talk about the thermodynamic analysis. Before we start, I would like to talk about processes involved. So the processes involved in this refrigeration cycle of an air conditioning system are the isotropic compression from step 1 to step 2 that occurs in the compressor, and then step 2 to step 3, which is constant pressure heat rejection that occurs in the condenser, and step 3 to step 4 where throttling occurs in the expansion valve, and step 4 to step 1 where constant pressure depression occurs in the evaporator. Before we start, I would like to just mention a few things in which the mass flow rate is 2.5 kilogram per second, and the refrigerant we're using is R134A. And we also have to identify the state in each of the processes. So for state 1, let's say we have a temperature of 2.5 degrees Celsius and pressure at 320 kilopascal, and we have to use the property table to identify the enthalpy and the entropy and use those to calculate the quality. So use that for state 1, state 2, and state 3, and state 4, and we have listed the values for each of it. And then we move on to the calculation. For the calculation, we are using the refrigerant quality of X at stage 4, and we found using the formula, the H4 minus HF over HFG, which is, and we got the value of 0.3185, and then we have a cooling load. We can see the calculation and we get the value of 335.25, and the work done by the compressor, which is 68.5 based on the calculation, and the heat rejected by the condenser, which is also equivalent to the compressor work plus the cooling load. It is known as, then we have the value of 403.75. And now we see the coefficient of performance, which is cooling load over work by compressor. And we got the COP of 5.19, which means that the cooling is 5.8. For every work done by the compressor is equivalent to 5.19 kilo cooling load. So now we enter the conclusion. The conclusion is that we have seen how we apply thermodynamic law 1 and law 2 in this refrigerant cycle, and also we understand that how does in general that how does each processes work in a pipeline of a refrigeration cycle and how it's always continuous. So that's all from us, and hope you understand from our video about how does aircon works in our house. So that's all. Thank you.